So, good day class. In this lecture, I'll be explaining isothermal system. Isothermal system. Okay. As I've said in my previous lecture, that the word iso means same. The word thermal means heat, but in form of temperature. So when the temperature in a given system is constant, the system is called an isothermal system. So take for example, let's say I have my container, I have the wire buoys which regulates the heat, I have the tripod stand, and I have my Bunsen burner. I have my piston which applies the pressure, and then my Bunsen burner which applies the heat in form of temperature, and I have the gases. But here the temperature is constant, okay, but the pressure is changing, the volume is changing. So if I apply pressure to this container, the volume is going to reduce, which gives a little space for the gases to collide more. It simply means the more the pressure on the gases, the more the collision rate. Okay, so that is why the law that governs an isothermal system is Boyle's law. And Boyle's law states that the volume of a given mass of a gas is inversely proportional to the pressure, provided that temperature is kept constant. So I'm having volume is inversely proportional to pressure, then V is equal to K over P, then K is equal to PV. So I can say P1, V1 equals P2, V2 in that respect. Okay, so this is the sequence that governs an isothermal system. Now, how do we get the work done in an isothermal system? We could remember that the change in work done for any given system is equal to the pressure times the change in volume. Now, in order to get the work done in an isothermal system, remember that the pressure is changing and the volume is also changing. Only the temperature is constant in this type of system that we are talking about. So in order to get the work done in an isothermal system, the first thing we have to do here is we have to recall the equation of an ideal gas, which is PV equals nRT. So this is equation of an ideal gas. So when we recall this, the next thing we are going to do is we make our pressure the subject of relation. So I'm going to have pressure equals nRT divided by the volume. Okay, it shows that anywhere I see pressure, I'm going to substitute this. So in that case now, I'm going to have the change in work done equals, I'll remove this and substitute this, nRT divided by V times the change in volume. Okay, now under differentiation, change in volume is always equals to dW, provided that the change in volume tends to 0, and also change in V is always equals to dV, provided that change in V tends to 0. So easily I can say dW equals nRT over V dV. So the next thing I'm going to do now in order to get my work done is I'm going to integrate both sides. So when I do that, I'm going to have integral of dW, in which the work done is starting from here, and then the initial work done is 0, equals integral of nRT over V dV, okay, in which the volume from the final, and then we are having the what? The initial. Okay, now the coefficient of this is 1. And when I integrate to 1 with respect to W, I'm going to have W. So this is going to be W. And then I have my upper limit and the lower limit equals. Now take a look at this. We want to integrate with respect to V. So nRT are constant. So I'll factorize that. So that will be nRT integral of the final volume, initial volume. Then I'm left with dV over V. Under the rule of integration, when I integrate 1 over V with respect to the V, I'm going to have lane V. So in that case, I'm going to have W, upper and lower limit, equals nRT, then this becomes lane V, and then I still have my upper and the lower limit. Okay, so the next thing I'm going to do is that I'm going to substitute the upper and the lower limit. So let's have it. So now if I substitute the upper and the lower limit, the rule of integration, that will be upper limit minus the lower limit. So anywhere I see W, I'm going to substitute W. So that will be W minus, anywhere I see W, I'll substitute the lower limit 0. So that will be 0 equals nRT into bracket. Anywhere I see V, I'll substitute the final volume. So that will be lane V, the final volume. And anywhere I see V again, I'll substitute the initial volume. That will be minus lane VI. Okay? So W minus 0 is W, which is the work done in an isothermal, equals, okay, nRT. Now, this is lane, which is natural logarithm. Okay, in logarithm, when we have negative, what do? We pick one of the log and we divide the what now? The alphabet or the number. So this becomes what? Lane into bracket the final volume divided by the initial volume. Okay, so this is work done in an isothermal equals nRT lane of what? The final over the what? Over the initial. So this is the formula that we use in calculating the work done in an isothermal system. So anytime they want us to calculate the work done in an isothermal system, they would have given us the what? The N, the number of molecules of the gases. Our R is constant. If it is in joule, that will be 8.314. And then it will give us the what? The constant temperature. Okay? We'll be given the what? The final volume and the initial volume, and then we'll be able to calculate that. Sometimes we might not be given the final volume and the initial volume, but we can still recall from Boyle's law that P1 V1 is equal to P2 V2. So in that case, we can make the final volume and the initial volume the subject of relation, so that we can just substitute our pressure here. Okay, so basically what I'm trying to say is, if we are not given the final volume and the initial volume, let's say we are given the final pressure and the initial pressure, all we have to do is we just have to recall, that P initial V initial is equal to P final V final from our Boyle's law. Then if I make my V final and V initial the subject of relation, I'm going to have V final over V initial equals P initial over what? P final. Then I can remove this and substitute this. So I can also have the work done in isothermal, so it equals to nRT natural logarithm. Instead of V final over V initial, that will be P initial over P final. So we can also have this formula for our isothermal. And sometimes we might not be given the number of molecules and the temperature. So if you're not given that, all we have to do is to recall also that PV equals nRT. Okay, we recall that PV is equal to nRT. So it simply means nRT is the same thing as PV. So I can also say the work done in isothermal is equal to, so instead of nRT, I can also have my PV. But it's not going to be just PV. Okay, it's going to be the P initial, V initial, natural logarithm of maybe this or this, any of the two. So that is going to be Pi over what? Pf. Or work done in isothermal is equal to Pi, Vi, lane of what? V final over what? V initial. So these are the formula that we use in calculating the work done in an isothermal system, depending on the parameters given in the question. In my next class, I'm going to explain adiabatic system. Thank you very much.